SpaceX's 10th Starship test flight just changed everything we thought we knew about rocket development. While previous flights ended in spectacular explosions that dominated headlines, Flight 10 quietly achieved something far more significant. The first truly successful upper-stage flight in Starship history. But here's what SpaceX isn't telling you about the anomalies they discovered during this milestone mission. From a mysterious engine failure at the worst possible moment to a deliberate crash landing that revealed critical data, this wasn't just another test flight. It was a masterclass in engineering validation that sets up Starship for missions we haven't even heard about yet. And that satellite deployment test? It almost went catastrophically wrong in a way that could have changed SpaceX's entire Starlink strategy. Starship's 10th integrated flight has been hailed as the most successful demonstration of this next-generation rocket system to date. Unlike many of the earlier attempts that ended in fireballs or mid-air disintegration, this test managed to stay intact all the way through its mission profile. But calling it successful doesn't mean it was flawless. What made this test so fascinating was that, while the rocket didn't meet a fiery end, it revealed several strange anomalies and produced a treasure trove of data that SpaceX engineers can now study. Think about where we were just a few flights ago. The first integrated test exploded on the pad. Later flights barely made it through ascent before catastrophic failures shut everything down. Each time, Starship proved that even a partial success could still move the development program forward. But this 10th attempt marked a turning point. For the first time, the rocket didn't just survive its major phases. It demonstrated that SpaceX can push Starship further than ever before, closer to its intended role as a fully reusable orbital-class vehicle capable of transporting humans and cargo to the Moon and Mars. The fact that it didn't explode is already a milestone. In the Starship program, survival itself is newsworthy. Yet what makes this flight stand out isn't just the absence of destruction, but the presence of subtle, surprising events along the way. These are the kinds of events that don't make headlines like a fireball in the sky, but to engineers and spaceflight enthusiasts, they're just as exciting because they show how much progress is being made and also how much remains to be solved. From the moment the engines roared to life, this test felt different. The rocket sat on the pad for a few seconds longer than usual before lifting off, almost like SpaceX was deliberately pausing to measure every vibration, every plume of exhaust, every piece of performance data before committing to flight. This was not a show launch designed to impress the public. It was a deep engineering experiment, and SpaceX wasn't afraid to take risks. And those risks paid off. For the first time, both the booster and the upper stage went through extended test sequences, pushing the vehicle into new territory. The booster performed maneuvers designed to stress test its aerodynamics, while the Starship upper stage completed a full ascent and engine shutdown, coasted through space, deployed its experimental payload dispenser, reignited its engines, and survived a fiery re-entry before splashing down nearly on target. That is an enormous leap compared to where the program started. But most successful does not mean problem-free. Along the way, viewers noticed anomalies, an engine failing at high altitude, an unexplained blast inside the upper stage, engine bay, and dramatic changes in the ship's color during re-entry. Each of these moments raised new questions. Why did a rear flap start tearing apart before the ship even hit the thickest part of the atmosphere? Why did parts of the rocket glow orange when the heat shield tiles were supposed to stay black? And what exactly caused that sudden explosion inside the engine bay that shredded parts of the hull without destroying the entire ship? These are the mysteries that make this test so valuable. Every anomaly is another lesson, another opportunity to refine the design. SpaceX isn't aiming for perfection on test flights. They're aiming for maximum learning. And in that sense, Flight 10 was a gold mine. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries. Give this video a like so we know to keep uncovering them. The broader significance here is that Starship has finally crossed a psychological barrier. It's no longer the rocket that always blows up. It's now the rocket that can complete a mission profile and still come back down in one piece, even if it's damaged. That is the foundation SpaceX needs to build upon if Starship is ever going to achieve Elon Musk's vision of regular, routine flights to orbit and beyond. So while the casual observer might just see a rocket didn't explode this time, those who follow the program closely see something much bigger. Proof that SpaceX's relentless trial-and-error approach is paying off, and that the dream of a fully reusable spacecraft is inching closer to reality with each fiery, unpredictable, and groundbreaking test. Every rocket launch has a moment that makes even the most confident engineers hold their breath. For Starship, that moment is called Max Q, the point of maximum aerodynamic pressure. This is when the rocket is moving so fast through the atmosphere that the combined forces of speed and air density create the highest mechanical stress on the vehicle's frame. It's a brutal moment for any spacecraft, and if something is going to snap, buckle, or malfunction, Max Q is often the breaking point. On Starship's 10th test flight, all seemed normal at first. The super-heavy booster, with its cluster of Raptor engines, thundered away from the launch pad, punching through the lower atmosphere. But then, just after clearing Max Q, something unusual happened. One of the booster's engines failed. Now, a single engine failing on a rocket with dozens of engines isn't necessarily catastrophic. In fact, Falcon 9 and Falcon Heavy have proven that SpaceX rockets can keep flying even if one or more engines cut out. That's part of the design philosophy. Redundancy ensures that the loss of one engine doesn't doom the mission. But what made this failure stand out was the timing and the altitude. Typically, when we've seen Raptor engines fail on test flights, the problems happen either on the launch pad or very early in ascent, while the rocket is still climbing through thick air and at relatively low speeds. Sometimes engines don't even light in the first place. Other times they flame out in the lower atmosphere. This time, however, the failure occurred higher up, right after passing through Max Q. That's a new wrinkle we haven't seen before. Why? Does this matter? Because Max Q isn't just tough on the structure of the rocket, it's also a critical moment for the engines. To survive it, the Raptors throttle down, easing off their power to reduce the stress on the vehicle. Then, once the booster clears the worst aerodynamic forces, the engines throttle back up, unleashing their full thrust to continue the climb into space. It's in that transition, from throttling down to throttling back up, that something seems to have gone wrong. Was it a hardware problem? Possibly. Restarting full thrust after throttling down is a complex maneuver, and any tiny imperfection in the engine's components, valves, pumps, or pressure lines, could cause a failure. But there's another possibility. SpaceX may have done this on purpose. SpaceX has a long history of deliberately pushing its vehicles to the edge, forcing failures just to see what happens. On earlier flights, they intentionally tested extreme re-entry angles that stressed the booster to the point of structural bending. So, it's entirely plausible that on Flight 10, they wanted to know how the rocket would behave if it suddenly lost an engine right after Max Q. In other words, this might not have been an accident. It might have been an experiment, and if it was, then the results were actually encouraging. Despite losing one engine, the booster kept flying smoothly. Its trajectory didn't wobble. It didn't spin out of control. It stayed the course and continued delivering the Starship upper stage on its way to orbit. That's exactly the kind of resilience SpaceX is designing for. If Starship is going to carry humans to Mars one day, it has to be able to shrug off failures like this without endangering the mission. So whether this was a real malfunction or a planned test, the lesson is the same. Starship proved it can handle losing an engine at one of the most stressful points of flight. That may not sound dramatic compared to fiery explosions, but in the world of rocket science, It's huge. It shows that the E2E Super Heavy booster's redundancy and control systems are working exactly as intended. It also raises new questions for engineers to investigate. If it was unplanned, what exactly caused the engine to shut down? Was it fuel flow? Was it thermal stress from the rapid throttle up? Or was it an electrical or software glitch? If it was intentional, what did the data show about the booster's ability to maintain stability and thrust balance? Either way, Flight 10 gave us a glimpse into how SpaceX is not just building a rocket, but stress testing a system designed to withstand the unexpected. One engine failing at max Q could have been disastrous. Instead, it was a reminder that Starship is being built to expect failure and to fly through it anyway. One of the most fascinating aspects of Starship's 10th test flight wasn't just how it left the pad, but how its massive Super Heavy booster came back down. Many people expected SpaceX to try something spectacular, like a dramatic tower catch with the giant Mechazilla arms, but that wasn't the plan this time. Instead, SpaceX focused on testing aerodynamics, specifically how the booster behaves when it re-enters the atmosphere at different angles of attack. Now, to understand why this matters, let's rewind to Flight 9. During that test, SpaceX pushed the booster into an extremely steep re-entry angle of about 17 degrees. Instead of falling straight down like a dart, the booster was angled like a javelin cutting through the air. The idea behind this is pretty clever. By flying at an angle, the rocket creates much more drag, which slows it down before the engines have to fire for the landing burn. That saves precious fuel, and it also gives the booster the flexibility to glide further downrange, opening up new options for flight paths and landing zone. But Flight 9 showed just how punishing this maneuver can be. The drag created so much stress on the booster's structure that it literally bent parts of the rocket. One of the critical pipes that channels fuel from the top tank to the engines was warped out of alignment. So, when the engines tried to reignite for landing, the fuel couldn't flow properly, and the whole system failed in a dramatic explosion. It was a classic case of learning by breaking. That brings us to Flight 10. This time, SpaceX dialed things back. They still flew the booster at an angle, but not as aggressively as before. The shallower angle reduced the aerodynamic drag just enough to keep the rocket intact, avoiding the kind of structural damage that doomed the previous attempt. The result? When it came time for the landing burn, the engines restarted cleanly, and the booster performed far better than before. This wasn't about showing off. It was about carefully stepping forward, finding the balance between pushing the envelope and keeping the hardware alive long enough to gather meaningful data. And that's what made this test so valuable. SpaceX now knows the booster can handle angled re-entries without collapsing under the pressure, at least at these more moderate settings. That means they can fine-tune the profile over future flights, inching closer and closer to the ideal combination of speed, efficiency, and structural safety. Skipping the tower catch may have disappointed some spectators, but from an engineering perspective, it was the right call. The point of Flight 10 wasn't to risk billions of dollars of infrastructure on a risky catch maneuver. It was to understand how the booster itself behaves under controlled stress. Once SpaceX has that data locked down, they'll have the confidence to try catching it with Mechazilla. So, while it might not have ended in a spectacular grab by the launch tower, the booster's re-entry on Flight 10 was still a huge win. SpaceX demonstrated that they had learned from Flight 9's mistakes and adjusted their approach. And perhaps most importantly, they showed that the Super Heavy booster can be flexible and resilient, adapting to different re-entry profiles without falling apart. This is the kind of incremental progress that often goes unnoticed by casual viewers, but is absolutely essential for building a reusable rocket system. Flight 10 proved that controlled experimentation with re-entry angles is not only possible but also effective in pushing the program forward. Each adjustment teaches SpaceX more about how to safely bring down the largest and most powerful booster ever built. one step closer to the day when it won't just fall into the ocean, but land gracefully back at the launch site, ready to fly again. The landing phase of Starship's Super Heavy booster has always been one of the most captivating parts of any test flight. It's not just about bringing the rocket back down. It's about proving that this towering 70-meter steel giant can perform delicate maneuvers with surgical precision after enduring the violence of launch and re-entry. And on Flight 10, SpaceX tried something particularly bold during the final descent. Instead of going with the standard landing profile, where the central engines reignite to slow the rocket and guide it to a controlled touchdown, SpaceX decided to simulate what might happen if one of those engines failed. Normally, the core engines are the most reliable for this stage, providing stable thrust right through the center of mass. But what if one of them went offline? Could the booster still maintain control and land safely? To answer that, SpaceX shut down one of the core engines and substituted it with a mid-ring engine. This is unusual because the mid-ring engines aren't positioned directly under the rocket's center of gravity. Firing them during landing creates an off-balance thrust pattern, something that could easily send a 5,000-ton booster tipping or spinning out of control. Yet, when Flight 10 reached its landing burn, that's exactly the configuration SpaceX tested, and the results were eye-opening. The booster reignited, fired its engines, and began its final descent. Despite the asymmetric thrust, it held itself steady. It hovered briefly over the Gulf of Mexico, balanced like a massive steel ballerina on jets of fire, before cutting its engines and plunging into the ocean in a controlled splashdown. This was not a failure. In fact, it was exactly what SpaceX had planned. The booster wasn't supposed to be caught by the launch tower or recovered at all. The current generation of super heavy hardware, the Block 2 design, has nearly reached the end of its testing cycle. SpaceX is already building the upgraded Block 3 boosters with lighter structures, improved engines, and optimized plumbing. That means the existing hardware is expendable, and the company can afford to push it to its limits with risky experiments. Like this? By proving that the booster can remain stable even when using an off-center engine for landing, SpaceX gained crucial data. This kind of resilience is essential for future missions. When you're dealing with dozens of engines, failures aren't just possible, they're inevitable. If Starship is going to be the backbone of lunar and Martian transport, it has to demonstrate that it can survive those failures gracefully, even during the most delicate moments of flight. So, Flight 10's landing wasn't about a dramatic catch or a triumphant return to the launch pad. It was about building confidence that Super Heavy can stay in control under adverse conditions. Watching a skyscraper-sized booster hover stably above the ocean on an intentionally imbalanced thrust configuration is more than just impressive. It's proof that SpaceX is designing for the real world, where perfection is rare and reliability comes from preparing for the unexpected. When the booster finally cut off its engines and slipped into the Gulf, it marked the end of its career. But it also marked a beginning. The data gathered from that descent will flow directly into the design of the V3 boosters. These new vehicles will be lighter, stronger, and far more capable, standing on the shoulders of every experiment and failure that came before. Flight 10's booster may now rest on the ocean floor, but its lessons will live on in every future Starship launch. While the booster drew plenty of attention during Flight 10, the real story unfolded higher up, with the Starship upper stage. For the first time in the program's history, the ship itself achieved a complete ascent, executed a clean engine shutdown, and then coasted through space in orbit. This wasn't just another incremental test. This was the first time we can say that a Starship upper stage completed a mission profile from liftoff to orbit and beyond. In earlier flights, Starship had always come up short. Either the engines didn't perform as expected, or the vehicle suffered catastrophic failures before reaching orbital velocity. Sometimes the ascent went smoothly, but re-entry proved fatal, with fiery breakups over the Gulf of Mexico. Flight 9 for instance, ended with the ship burning up after struggling to control its descent. Each of those attempts provided data, but none could be considered a full success. Flight 10 changed that. After separating cleanly from the booster, Starship's 6 Raptor engines carried it higher and faster than ever before. The climb was steady, the engines burned as planned, and when the cutoff command was given, everything happened exactly on schedule. For the first time, Starship achieved a proper orbital insertion. Then, as it coasted silently through space, we witnessed a moment that SpaceX engineers have been chasing for years. A functioning, fully intact Starship, gliding above Earth, behaving just as it was designed to. The importance of this can't be overstated. Starship isn't just supposed to launch, it's supposed to operate in orbit. That means being able to coast, maintain attitude control, and remain stable for extended periods. Flight 10 demonstrated all of that. The ship didn't tumble uncontrollably, it didn't leak propellant, and it didn't experience structural failures during the coast phase. For the first time, we saw Starship not just as a prototype, but as a working spacecraft. Adding to the milestone was a small but symbolic payload test. Instead of carrying actual satellites, Starship V2 deployed a set of test objects using what's known as the PEZ Dispenser system, a mechanism designed to release Starlink satellites into orbit. Watching the system operate successfully confirmed another critical piece of the puzzle. Starship isn't just capable of reaching orbit, it's capable of delivering payloads once it gets there. This single step is the foundation for everything SpaceX hopes to achieve with the program. Lunar landings, Mars missions, point-to-point transport on Earth, all of it starts with a reliable upper stage that can function in orbit. With Flight 10, that dream moved out of the realm of theory and into demonstrated reality. For SpaceX, this was the moment where Starship stopped being just an experimental rocket and started proving itself as a viable spacecraft. It was the first time the vehicle did exactly what it was designed to do: climb into space, shut down its engines, and remain operational while orbiting Earth. That may sound like a simple checklist, but in rocketry, getting all 3 of those steps right is the difference between a concept and a true success. Flight 10 will be remembered not just for its lessons about boosters and re-entry profiles, but for this milestone, the day Starship, in its second-generation form, proved it could go to space and stay there. Reaching orbit was a milestone in itself, but SpaceX used Flight 10 to prove something even more critical: Starship's ability to deliver payload. After all, it doesn't matter how powerful a rocket is if it can't actually deploy satellites or cargo once it gets to space. That's why this mission carried one of the most anticipated demonstrations yet: the debut of the Starlink PEZ Dispenser system. The concept behind it is deceptively simple. Instead of using complex mechanical arms or ejection pistons, Starship is designed with a massive internal bay and a sliding door. Inside, satellites are stacked in neat rows. When it's time to deploy, the door opens, and the ship gently pushes the satellites out one by one, just like candy sliding from a PEZ dispenser. It's elegant, efficient, and perfectly tailored for Starlink, where hundreds of satellites may need to be released in rapid succession. On Flight 10, SpaceX tested the mechanism using dummy satellites, mock-ups that matched the size and mass of the real thing, but carried no electronics. As the dispenser activated, the first payload smoothly drifted out into the void. Then another followed, and another. It was a surreal sight. Starship, still fresh from its first clean orbital insertion, quietly demonstrating its ability to deliver cargo into space. Not everything went perfectly. At one point, one of the mock satellites clipped the edge of the payload bay door as it exited. It wasn't a catastrophic impact, more of a bump than a crash, but it was enough to catch the attention of engineers reviewing the footage. In the real world, even a minor collision like that could scratch or dent a satellite. potentially compromising its performance once deployed. But in testing, little imperfections like this are golden. That single clip gave SpaceX valuable data about tolerances, clearances, and timing. It may mean the deployment mechanism needs a slight adjustment in angle, or that the door needs a fraction more clearance. These are exactly the kinds of refinements that can only be discovered in real-world conditions, and SpaceX now has the data to make the system even more reliable. Overall, the test was a success. The dispenser worked as designed, releasing satellites smoothly and without mechanical failure. For SpaceX, this validated the core concept. Starship can carry and deploy Starlink satellites directly into orbit. And that's not just a small win. It's the key to the company's entire long-term business model. Starlink is the financial backbone of SpaceX's Mars ambitions. Every satellite launched increases global coverage. Every customer signing up provides revenue, and every revenue stream helps fund the colossal expense of developing Starship. That's why proving this dispenser system is so important. With it, SpaceX won't need Falcon 9 to deploy Starlink anymore. Starship could do the job faster, cheaper, and in much greater numbers, potentially launching hundreds of satellites in a single flight. The PEZ dispenser test may have seemed like a small detail in the grand narrative of Flight 10, but in reality, it was one of the most consequential demonstrations of the mission. It showed that Starship isn't just a giant rocket, it's a fully integrated cargo system capable of carrying payloads into orbit and deploying them with precision. And while this was only a test with dummies, the implications are enormous. Next time, those satellites won't be mock-ups. They'll be real Starlinks, joining the growing constellation that's already transforming internet access around the globe. Perhaps the single most important moment of Flight 10 came not during ascent, not during payload testing, but during the silence of orbit. Hours after launch, as Starship drifted high above Earth, engineers commanded a maneuver that could determine the future of the entire program, restarting the Raptor engines. In space, on the surface, this might not sound dramatic. Engines start, engines stop. That's what rockets do. But in practice, reigniting a rocket engine in orbit is one of the hardest challenges in aerospace. It's not the same as firing engines on the launch pad, where gravity and stable fuel flow help. In orbit, fluids don't behave like they do on Earth. Propellant can slosh unpredictably. Bubbles can form in the lines, and without careful management, an engine restart attempt can sputter and fail. For Starship to succeed in its long-term goals, whether it's ferrying satellites, landing on the Moon, or making the journey to Mars, it must prove it can reliably restart its engines outside the atmosphere. On Flight 10, that's exactly what happened. For the first time, the Raptor engines lit up again in space. The ignition was smooth, stable, and sustained, producing a clean burn that proved the systems for propellant management, ignition, and combustion all worked in microgravity conditions. It was a critical moment of validation, showing that Raptor isn't just a powerful engine on the launch pad, but a versatile one capable of multiple restarts, exactly what's needed for orbital maneuvering and eventual interplanetary missions. The importance of this can't be overstated. Without a reliable Relight, Starship would be a one-way rocket, capable of reaching orbit, but unable to come back down safely. Every re-entry, every precision landing, every future mission depends on the ability to fire the engines again in space. The deorbit burn is non-negotiable. Without it, Starship can't lower its orbit and re-enter the atmosphere in a controlled manner. With it, the ship becomes a truly reusable spacecraft. This was also a milestone for future refueling operations. SpaceX's vision of interplanetary travel hinges on Starship being able to rendezvous in orbit with tanker versions of itself, transferring fuel and then reigniting to head for the Moon or Mars. A failed Relight would make that dream impossible. Flight 10 proved that the Raptor system is up to the challenge. In many ways, this quiet engine restart was just as significant as Starship reaching orbit in the first place. It was the missing link between getting to space and coming home again. And because it worked, SpaceX now knows they have a foundation they can build on. For Flight 10, the Relight paved the way for a safe, controlled deorbit burn. For the future, it opens the door to everything else: cargo flights, crewed missions, lunar landings, and interplanetary voyages. It was a simple test, but a decisive one. Starship has shown it can fire its engines in the vacuum of space, on command, reliably, and safely. That's the moment SpaceX engineers have been waiting for. Re-entry has always been the dragon that Starship must slay, no matter how successful. A launch, or how smooth an orbital burn, the return to Earth is where so many test flights have ended in fire. Flight 10 was no exception. It pushed the ship through the brutal physics of atmospheric re-entry, exposing both its strengths and its weaknesses in spectacular fashion. The first thing to note was how well the forward flaps performed. These have historically been one of Starship's weakest points. In earlier flights, the forward flaps, those large aerodynamic control surfaces near the nose, buckled, overheated, and even tore apart under the extreme stress of re-entry. But this time, they held. Reinforcements and refinements paid off, and the forward flaps cut through the upper atmosphere without catastrophic failure. That's a major improvement, showing that SpaceX has begun to solve one of Starship's most persistent vulnerabilities. But while the front end held together, the rear flaps told a different story. As the ship dove deeper into the atmosphere, the heat shield and tiles glowed an angry orange, and the rear control surfaces started taking the brunt of the fiery descent. Cameras captured pieces of material glowing, charring, and finally melting away. At one point, entire sections of the rear flaps appeared to be compromised, exposing the underlying structure to direct plasma heating. This wasn't just cosmetic damage. It was the kind of thermal assault that could cripple a spacecraft if not addressed. And then came the blast. Deep in the belly of the ship, inside the engine bay, a violent explosion ripped through. Flames and debris spewed outward as part of the ship's plumbing or structural supports gave way. The blast shredded parts of the lower hull, leaving jagged openings that glowed with re-entry plasma. For a moment, it looked like Flight 10 might end the way so many earlier attempts had, in total destruction. But remarkably, Starship endured. Despite the damage, despite the shredded panels and molten rear flaps, the ship kept flying. It held its orientation through the atmosphere, using what remained of its control surfaces to maintain stability. Even with the engine bay torn open, Starship refused to spin out of control or disintegrate mid-descent. That resilience alone marks an enormous leap forward from earlier flights, where similar failures sent the vehicle tumbling to its fiery death. For engineers, this was a goldmine of data. The fact that the forward flaps survived means design improvements are working. The fact that the rear flaps melted tells SpaceX exactly where to focus the next round of upgrades. Whether it's stronger materials, better cooling, or new shapes to shed heat more effectively. And the engine bay blast, while dramatic, is the kind of stress test that reveals hidden weaknesses in plumbing and structural design. Weaknesses that can now be fixed before future missions. In rocketry, survival is sometimes more valuable than perfection. Flight 10 proved that Starship can take severe punishment and still make it through the atmosphere in one piece. The rear flaps may have melted, and the engine bay may have been torn apart, but the ship itself lived to complete its mission. That's a testament to the strength of the design and a promise of how much further it can go once those weak spots are addressed. Re-entry remains the hardest test of all. But, for the first time, Starship has shown that it can fight through the fire, endure the damage, and come out the other side still flying. One of the most visually striking moments of Flight 10 came during the final minutes of descent, when Starship began to change color before the eyes of millions watching online. As the spacecraft plunged through the atmosphere, cameras captured an almost surreal sight. The top half of the ship glowing a brilliant white, while the bottom half radiated an intense orange hue. It was as if Starship itself was catching fire. But in reality, this was a controlled experiment in materials science. Elon Musk later explained that this dramatic color shift was caused by experimental heat shield materials being put to the ultimate test. The white areas were coated with ceramic insulation designed to withstand extreme temperatures. As the ship descended, the outer layer of ceramic vaporized, creating a cloud of white particles that temporarily coated nearby tile. This process wasn't destructive. It was intentional and provided valuable data on how the ceramic responds to real atmospheric entry conditions. The orange glow on the lower half of the ship came from a completely different process. Some tiles were constructed from metal test alloys designed to measure oxidation under extreme conditions, when exposed to the atomic oxygen high in the upper atmosphere and the intense heat generated during re-entry. These metal tiles began to oxidize rapidly, essentially rusting in real time. The result was a striking orange color, creating a visually dramatic contrast with the pristine white ceramic above. This wasn't just for show. Each color change represented critical engineering data. The vaporization of the white ceramic revealed how the material protects underlying structure and how particles disperse in real time, which informs future design. Meanwhile, the metal tiles allowed engineers to study oxidation patterns and heat absorption under real flight conditions, helping refine the balance between weight, protection, and cost for future heat shield iterations. From a broader perspective, the color change was also symbolic. Starship, after 10 integrated flights, is still very much in the experimental stage. It's a spacecraft that can survive launch, orbit, engine relight, and re-entry, yet it continues to evolve with every test. The glowing orange and white isn't just a visual spectacle. It's a visible marker of innovation, showing that every part of the vehicle is actively learning, testing, and adapting in real time. For spectators, it looked like a spacecraft literally glowing from the heat of atmospheric friction. For SpaceX engineers, it was a treasure trove of data, proving that their experimental heat shield strategies work in practice and giving precise clues about where improvements are still needed. In essence, Flight 10 wasn't just about reaching orbit or surviving re-entry. It was about turning Starship into a living laboratory in the sky, visible for all to see. The color-changing effect might have dazzled audiences, but for SpaceX, it was a concrete success, an unplanned light show that told the team exactly how the ship behaves under the most extreme conditions. After surviving the fiery re-entry and dramatic color changes, Starship faced its final test, the landing, or, in this case, the intentional splashdown. Even with rear flap damage and a partially shredded engine bay, the spacecraft demonstrated astonishing precision. Cameras and telemetry confirmed that Starship touched down within just 3 meters of its intended target in the ocean. This level of accuracy is unprecedented for a vehicle of this size and complexity, and it shows just how much control SpaceX has gained over Starship's aerodynamic systems, even in less than ideal conditions. Landing precision is about more than bragging rights. For future missions, whether delivering satellites, performing crewed flights, or attempting point-to-point Earth transport, accurate landings are essential. They minimize recovery costs, reduce the risk of damage, and allow engineers to reuse hardware more reliably. Flight 10 proved that Starship can handle its descent and still meet strict targeting requirements, even while sustaining structural damage. Looking ahead, Elon Musk has hinted at the next phase of testing, the first tower catch attempt, where the booster will be caught by mechanical arms on the launch tower instead of splashing into the ocean. This maneuver is planned for somewhere between flights 13 and 15, and it represents the next big leap toward rapid reusability. Catching the booster intact would eliminate the need for ocean recovery and mark a milestone in the Starship program's long-term vision. Flight 11 is expected to continue using the current V2 design, allowing engineers to refine systems and apply lessons learned from Flight 10. But the real excitement lies just around the corner. V3 Starships, equipped with upgraded Raptor 3 engines are expected to arrive within the next 3 to 4 weeks. These new ships promise higher thrust, improved reliability, and enhanced efficiency, key elements for reaching full orbit and performing the complex maneuvers required for tower recovery tests. Taken together, Flight 10 has propelled the Starship program closer than ever to operational status. Engineers now have actionable data on booster re-entry angles, flap performance, engine relight, heat shield behavior, and landing accuracy. Every anomaly and every success feeds directly into the rapid iteration process that SpaceX is known for. With V3 ships and Raptor 3 engines on the horizon, the program is entering a phase where full orbit flights, tower catches, and eventual missions to the Moon or Mars are not just theoretical. They are actively being tested and realized. In short, Flight 10 wasn't just a successful test flight, it was a proof of concept for a reusable, reliable, and precision-controlled spacecraft. Starship has survived the gauntlet of launch, orbit, re-entry, and landing, and the next flights will push it even further, bringing Elon Musk's vision of a fully operational Starship fleet tantalizingly close to reality. Flight 10 has proven that Starship is no longer just a concept. It is a spacecraft capable of surviving the full spectrum of stresses from launch to orbit, from engine relight to fiery re-entry, and down to precise landing accuracy. Each success and anomaly has provided SpaceX with a treasure trove of data, fueling rapid improvements and guiding the next generation of Starships. The experimental tests, the booster re-entry angles, engine shutdowns, color-changing heat shields, and precision splashdown show that every element of Starship is being rigorously tested in real conditions. While there are still challenges to solve, such as rear flap durability and engine bay protection, Flight 10 proves that SpaceX can learn, adapt, and overcome obstacles faster than ever before. Looking forward, the program is entering an exciting phase. V3 Starships with upgraded Raptor 3 engines will take the lessons of Flight 10 even further, enabling full orbital flights, the first tower catch attempts, and eventually missions beyond Earth orbit. Flight 10 has laid the foundation for reusability, precision, and reliability, bringing humanity closer to a future where space travel is routine, ambitious, and transformative. For SpaceX, this is more than a test. It's a stepping stone to the stars. Starship's journey is just beginning, but Flight 10 has shown the world that the dream of rapid, reusable, and interplanetary spacecraft is no longer science fiction. It's happening before our eyes. The sky is no longer the limit. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.